Hi there. In this video, we're going to have a look at exact trigonometric ratios or exact trigonometric values. Now, a trig ratio is really just the output, the result from working out the sine, cosine, or tangent of an angle. Um, an exact value or exact ratio is when we don't approximate it. We leave it, for example, with a square root sign or something else in it rather than approximating to a decimal. And in trigonometry, there are some angles that appear so often in real world contexts that we tend to try and know them off by heart. I have to say that these common angles and their trig ratios are in fact given to you on your information sheet. And the reason why we're doing this video is to give you a really good grounding on how these exact trig ratios are calculated, uh, so that you understand where it all comes from. And my experience is that makes you a better mathematician overall, even if you've got an information sheet to support you. So the common angles we're going to look at are 30 degrees, 60 degrees, and 45 degrees. In radians, that's pi on 6 for 30, pi on 3 for 60, and pi on 4 for 45 degrees. They're so common, you will learn them eventually. You might notice they're out of order. That's because 30 and 60 are what we call complementary angles. They add up to 90 degrees. So they kind of go together a lot. We're going to have a look at 30 and 60 degrees first. And I've started the ball rolling by creating a equilateral triangle. An equilateral triangle. An equilateral triangle has three sides of the same length and therefore three angles that are the same size. And since the interior angles of a triangle equals 180 degrees, every single angle in this triangle must therefore be 60 degrees, 180 divided by 60. Now, it turns out that if you drop what we call drop a perpendicular, that means a line that goes from the top of the triangle down to the bottom of the triangle at right angles to it, hence perpendicular. If we do that in an equilateral triangle, we bisect the angle at the top here. Bisect means cut into two exact halves, which means that this angle here is 30 degrees. And we also bisect the side length down here. So since it's equilateral with a side length of 2, this will get cut into a side length of 1 here and a side length of 1 here. We're only going to be focusing on this left-hand side triangle, but it's important to see the whole context. I'm going to zoom out so we can do the rest of it. What we're missing is the height of the triangle. And we need the height of the triangle because what I'm going to be doing next is focusing on this triangle here, which is a right-angled triangle. So we're going to use Pythagoras' theorem, which is that c squared, the hypotenuse, is equal to a squared plus b squared, the sum of the two other sides. Now the hypotenuse is 2, which means that c squared is 2 squared. The bottom has been halved, so now it's 1 squared. And the other thing we don't know is the height, so that's h squared. So I'm now going to subtract 1 squared from both sides. So that's going to be 4 minus 1 is equal to 8 squared, which means that h squared is equal to 3 and h is equal to the square root of 3. So now we have our three side lengths. We have a side length of 2, a side length of 1, and a side length of the square root of 3. There you go. What we're now going to do is we're going to use basic trig SOHCAHTOA principles in order to come up with the sine, cosine, and tan of 30 and 60 based upon this little diagram here. So let's start off with 30 here. The sine of 30, SOHCAHTOA, must be opposite, which is 1, over hypotenuse, which is 2. So sine of 30 is opposite 1 over hypotenuse 2. It's equal to 1/2. And just to remind you, that would also be the sine of pi on 6. The sine of 60 is going to be starting here. So the opposite is now root 3, and the hypotenuse remains as 2. So we've got opposite root 3 over hypotenuse 2. And that, of course, is the sine of pi on 3. Cosine of 30 is adjacent root 3 over hypotenuse 2. The cosine of 30 is adjacent root 3 over the hypotenuse 2. And that's also equal to the cosine of pi on 6, the radian measure for 30 degrees. Cosine of 60 degrees is adjacent 1 over hypotenuse 2. So the cosine of 60 is 1 adjacent over hypotenuse 2. And that's equal to the cosine of pi on 3, the radian measure for 30 degrees. You might note that the cosine of 60 is the same as the sine of 30, a half. And the cosine of 30 is the same as the sine of 60, root 3 on 2. And that's because the sine of an angle is equal to the cosine of its complementary angle. 30 plus 60 is 90. 60 plus 30 is 90. So, for example, the sine of 10 degrees would be the same as the cosine of 80 degrees, and vice versa. Let's have a look at tan. SOHCAHTOA, tan is opposite over adjacent. If we're at the 30 degree point here, then opposite is 1 and adjacent is root 3. And so we have opposite 1 over adjacent root 3. But we're not quite finished yet, because in mathematics, we don't like to see an irrational number like square root of 3 as the denominator of a fraction. So we do what's called rationalizing the denominator. It's pretty straightforward here. I'm going to multiply the bottom by root 3, because root 3 times root 3 is equal to 1. And I'm also going to multiply the top by root 3, and that gives us our new looking fraction, which is square root 3 on 3. So the tan of 30 degrees is root 3 on 3, which of course is the same as the tan of pi on 6. This is possible because all I'm doing is I'm multiplying the top and the bottom of the fraction by the same number. It's a fancy number, root 3, but it is just a number. And therefore, this is an equivalent fraction, which means it's the same value, it just looks different. Tan of 60 is pretty easy. If I'm here, the opposite value is root 3 and the adjacent value is 1. And so the tan of 60 is root 3 over 1, which is simply the square root of 3. And of course, that's equal to the tan of pi on 3, the radian measure for 60 degrees. And that's it for 30 and 60. Here's another triangle to consider. This triangle is an isosceles triangle. If it's a right-angled isosceles triangle, then there's only 90 degrees left for these two, and we know that in an isosceles triangle, the base angles are the same, and therefore they both must be 45 degrees. You can see here that I've got a hypotenuse of 2, just like the other triangle, and I have two unknown sides. So let's label them as x for this side, and because it's an isosceles triangle, this must be x as well. So using Pythagoras' theorem, I'll have 2 squared, the hypotenuse, is equal to x squared, one of the sides, plus x squared, the other side. That gives me 4 is equal to, these are like terms, so it's just 2x squared. Therefore, x squared is equal to 2 by dividing both sides by 2, and x is equal to the square root of 2. That's the exact value instead of the approximate decimal. So we've got side length of root 2. That makes sine of 45 degrees opposite over hypotenuse. So that will be root 2 on 2. Cosine is adjacent over hypotenuse. So that is again root 2 on 2. And this works based upon what I was saying on the previous page. 45 degrees and 45 degrees, they are complementary. They add up to 90 degrees. And yes, the cosine and sine of the complementary angles are indeed the same value. Tan of 45 degrees is the last one to do. Tan is opposite over adjacent. So that's going to be opposite root 2 over adjacent root 2. And that is equal to 1. Doesn't matter what the value is other than 0. If it's that value over the same value, it's simply going to be equal to 1. So that's a nice, easy result. I should have also said that the sine of 45 degrees is the same as the sine of pi on 4, the radian measure. Similarly, the cosine of 45 degrees is the cosine of pi on 4. And lastly, the tan of 45 degrees is equal to the tan of pi on 4, the radian measure for 45 degrees. That's it for this video. In the next video, we'll have a look at some more exact values, which we can't use triangles to figure out. And we'll have a look at some examples about how to use this to solve problems.